Zeros of polynomial functions. We've been talking about the zeros already. The zeros are the solutions. Basically, you set the function equal to 0, solve for x. Those x values, we call them x-intercepts, or zeros, or roots, or even factors. They all mean the same thing. So here, just more of the same, but just trying to get a little bit more technical in terms of finding those so-called zeros. You got to remember from a few days ago, synthetic division. That's important. So that's it's the shortcut you remember for long division, but it gets you right there. So an easy way to check to see if a number is a zero, you just plug it into synthetic division, and if you get a 0 at the end, then that particular number is a 0. That's the idea there. So let's look at that. The first thing that we run into is called the rational zero theorem to find all possible rational zeros. So we got these rational zeros, but you could also have imaginary zeros. Well, this rational theorem test doesn't give us those irrational values. That is, the numbers with the imaginary unit I. But they do give us the rational, just the regular numbers, if you will. This rational zero theorem would give you all possibilities. All possibilities does not mean that all of these possible zeros are indeed all the zeros for that particular function. The zeros for that function would be a subset of all the possibilities. We may have, let's say, 10 possibilities, but you may only have actually out of that 10, maybe 2 of them are the actual zeros for that function. So from there, we try to find the zeros, solve these polynomial equations. The word solve an equation simply means, again, find the zeros. Because finding the solution to the equation, that simply means set the equation equal to 0, solve for x. So again, to solve the solution, that gives you the x-intercepts, that gives you the roots, that gives you the zeros. They all mean the same. A classic theorem that we run into here is the linear factorization theorem. Carl Friedrich Gauss, when he was about 21, some of the writings say 21, some say 22, he did his dissertation. His dissertation was to actually prove, nobody at that time, his 1700s, no one at that time was able to prove the factorization theorem. The linear factorization theorem says, before that, it alleged that any polynomial of nth degree should be able to be factored n times, which would include the general statement for all complex roots. So a complex root means that the roots could be imaginary and real, or all imaginary. Sounds great, makes sense, but at that particular time nobody could prove it. Gauss, and a lot of what we have in mathematics in terms of being able to write out a lot of the notations in math are attributed to Carl Friedrich Gauss. What Gauss did was to prove the linear factorization theorem was, he said, I don't have to prove for all n cases that a polynomial can be factored n times. He said, all I have to do is just prove it one time. He said, all I have to do is to show that I can take any polynomial of nth degree and just factor it one time. That is to find only one zero. And what Gauss said, if I do that, then what remains, apply that same principle to the remainder. And then whatever remains from that, apply that same principle. So basically, if you ever have dealt with computer programming, they have something called a recursive function. That is a do loop. Well, that concept comes here directly from the originators of computer science, which is the mathematics. And so Gauss said, look, if I can show one time, then we can get all n times after that by applying the same process. So what Gauss did was to actually, before he proved the linear factorization theorem, he actually proved the fundamental theorem of algebra, which simply says that any polynomial of nth degree has one complex root. Very fascinating. You apply that to the linear factorization theorem, and basically what you end up with is this. Say, for example, if you have a polynomial let's say it is some f of x, and this x looks like, let's say this is 3x to the third minus let's say this is 18x squared plus 3x. So what Gauss said is that we can do this. I can factor out a 3x because 3x is common in all three places. Right? And so, and we've been doing this. And then can we factor x squared minus 6x plus 1? Can we factor that? Well, all we're saying is if x squared minus 6x plus 1 equal to 0, then x is equal to 6 plus or minus the square root of 6 squared minus 4 times a times c all over 2a. So we get here x is equal to 6 plus or minus the square root of, here this is 36 minus 4, 32 all over 2. So we get x is equal to 6 plus or minus, looks like we can pull out, what is that, 16 times 2, so that's 4 times the square root of 2 all over 2. And that gives us 3 plus or minus 2 times the square root of 2. So we come back over here, we say that f of x is equal to three x times x minus 3 minus 2 times the square root of 2 times x minus 3 plus 2 times the square root of 2. So what do we call that? Factoring, right? That's all we did. And we've been doing factoring a long time. Middle school, high school. But the reason why we do that is because of, one, the fundamental theorem of algebra, which says that any polynomial of nth degree, here this polynomial here, the degree n is equal to 3. Right? Any polynomial of nth degree, the fundamental theorem of algebra says that I should be able to find one zero, one root. That is, I should be able to factor it at least one time. So based on that, what we get, the first case, is that x is equal to 0. And then now, based on what I have left, what do we have left? I have left this part right here. I should be able to factor that, hopefully at least one more time. And then whatever I have left, factor that one more time. So we factor this part, and we use here this quadratic formula, right? And that gives us two roots, right? We get x is equal to 3 plus 2 times square root of 2. Now, if you get everything on the same side, that's x minus 3 minus 2 times square root of 2. And we get x equal to 3 minus 2 times square root of 2. That is to say, so here, this is a factor, and this is x minus 3 plus 2 times square root of 2. It's also a factor. And so that's how I get this information there, that information there. So all I'm saying is this. You've actually been doing this for a very long time. But the question is, what the heck have you been doing? Probably nobody told you. And the concept that I understand when it comes to life itself and the philosophy of life is, why am I doing something? I don't know why the heck I'm doing it. Why? I don't know about you, but that was my fundamental question when I was coming up through grade school, which probably kind of showed why I flunked so many things from the first grade to the, 8th, 9th grade, because none of the teachers could tell me why the heck I was doing what I was doing. Didn't make any sense. So later on, I was able to get some of these questions answered. And so my thing was, I want to know exactly why am I doing this? Why does this make sense? What's the purpose of it? And then I don't mind doing it. But just doing stuff, just to be doing it, I mean, I was a kid, but to me that just didn't make any sense. So, if you've done arithmetic, I mean, why do arithmetic? Why? What is the fundamental concept? Did you not know that there's a fundamental theorem of arithmetic? And so today we talk about the fundamental theorem of algebra. And then in calculus, we have a fundamental theorem of calculus. We have two. And then in vector analysis, we have the fundamental theorem of line integrals. Go a little bit further. They all pretty much say the same thing. That's the fascinating thing. I mean, the complex fundamental theorems way out there in this math world, they all hinge on the fundamental theorem of arithmetic, which the more complex of all those theories is the fundamental theorem of arithmetic. That's the hardest one. Not all this complex stuff. So, and then after that, Rene Descartes. Anybody familiar with Rene Descartes? Have you heard of this name outside of mathematics? Here are the Descartes rule. Good morning. Descartes rule. So Rene Descartes. Anybody know who he was? What did he do? He put together a philosophical and mathematical spectrum called analytical geometry. He's said to be the originator of it. Probably wasn't, but he's the one that got credit for it. So he was also a philosopher as well. When you go to graph an equation on the XY plane, what do you call that XY plane? Anybody remember? Starts with, what's that?
The axis.
There's two of them. It's the x-axis and the y-axis. Okay. Wake up, Emmanuel. Where's your coffee, man? Have you ever heard of the Cartesian product? The XY plane is called the Cartesian product, named after Rene Descartes. Because philosophically, he said that any idea, any concept, is divisible into two parts. And he talked about a physical part, if you will, and he talked about a metaphysical, a mental state, or a spiritual, if you will. It doesn't matter. You get into Immanuel Kant with his metaphysics. But Rene Descartes said that any concept can be divided into two things, or even he said three, or possibly even more. Take you, for example. Take Michael. Michael has a body. He has a mind, right? The psyche, which in the Greek is the same word that we get for soul. But then he also has a spirit. So he has three parts. Now, if you don't like the spirit part, then you could say he has two parts. Take a point in the XY plane. Take the point, let's say the point P. It has x sub 1, y sub 1. 1 point, right? P is said to be found. Say we got some x sub 1 and some y sub 1. We get this 1 point. But that 1 point consists of two parts, right? An x part and a y part. Now this x part is said to be that which is in the natural realm. That's how Rene Descartes saw it. You know, that which we see with our naked eyes. But then he said, but that same component, that same P, this point, whatever you want to call it, also has some uplift to it that makes it rise or makes it fall. So I can take the x part, but then I can rise it up, or I can let it fall down. He called that the soul. And so you have the x-axis, which is that which we can see, but then you have this y-axis, that which we think. And so Rene Descartes talked about this idea of, have you heard of this phrase, mind over matter? Have you heard of that? So the matter is said to be the x part, and the mind is said to be the y part. What I want you to understand is that mathematics is not by itself in some spectrum that we just study all by itself. The early philosophers looked at mathematics as being the connection, the bridge to everything that we do. Je pense donc je suis. Descartes was a Frenchman. And he said, I think, therefore I am. He said, I think, that's the y part, therefore I exist. The existentialists, they took that to mean that existence in the present is Rudolf Bultmann, these existentialists. They took this mathematical concept and applied it to philosophy, to theology, oh man, to just everything. So now I digress and talk about easy stuff. So the rational zero theorem. The rational zero theorem says, given any polynomial, make the screen so you can see it better. Some polynomial f of x. It has all these terms. Look at that a sub n, and then look at the a sub naught. So look at the first, look at the last. I never thought about it like that. Look at the first and the last. So we look at the coefficients. They call it here P over Q, but it's simply, we're looking at the factors of here a naught over a sub n. And this would be all the factors, all possible factors. All the possible factors of a naught divided by a sub n are set to give us all the possible rational zeros for the particular polynomial. Let's see. All right, we're going to take this polynomial here, and so we're going to look at all the factors of. Let's list it. A naught is 4, and a sub n is -1. Right. So here, all of the factors of what they're doing is they're saying. Does he write it out? All the possible factors of that constant term, which is the 4, divided by the factors of the leading coefficient, which is the -1. And so you have all the factors of 4, which is plus or minus 1, plus or minus 2, plus or minus 4. And then all the possible factors of -1, plus or minus 1. And so what you're going to do is you're going to divide each term in the numerator by that term in the denominator. Well, this is just plus or minus 1, so it makes this going to be obvious. So that is, you're dividing by 1. 5 divided by 1 is just 5. So here you can just think about this as being just the numerator if I'm dividing by plus or minus 1. So not too much to do there. But all the possibilities would be plus or minus 1, plus or minus 2, plus or minus 4. So they're saying that the zeros for this particular function would fall from this big set. Right? Now the leading coefficient is -1. The degree is 4. So at max you can have 4 zeros. At max means you can have 4, you could have 3, you could have 2, you could have 1, you could have none. Again, the zero simply means where this function's graph crossed the x-axis. So the rational zero test doesn't tell us exactly which of these possible zeros are the zero. They just list all of the possibilities. Bless you. Here's another problem. I think this one is a little bit better. So we take all possible factors of, look at the -2 divided by the 15. So that becomes the plus or minus 1, plus or minus 2, all over plus or minus 1, plus or minus, look at the factors of 15, plus or minus 3, plus or minus 5, plus or minus 15. He has it right here. And then after you do that, then we're going to take each term in the numerator and divide it by the term in the denominator. So we'll take the plus or minus 1 divided by 1, that's just 1. Then take plus or minus 1 divided by plus or minus 3, we get the 1/3. Take the 1 divided by 5, we get the 1 plus or minus 1/5. And then the plus or minus 1 divided by 15, we get plus or minus 15. Then you take 2 divided by 1, you get plus or minus 2. 2 divided by plus or minus 3, we get plus or minus 2/3. 2 divided by 5, plus or minus 2/5. And then 2 divided by 15, plus or minus 2/15. I mean, it's a lot there, but they're saying the actual zeros fall within that. Now notice the rational zero test doesn't tell us exactly what they are. They do something else. Here's they get -1, -1/3, and 2/5. They do something else to actually figure out exactly which ones are they. Now what they do to determine that is just synthetic division. Right? So how do we determine the actual zeros for a particular function after using the rational zero test? Start with the smallest, and then I plug the smallest number into synthetic division. If the end result is 0, I get a 0. If not, I check another one. Okay? Let's see. All right. So here, find all zeros. So don't use synthetic division. Just list out. I'm going to give you a second. I'm going to step out. Just list out all the possible factors. All right? Using that rational zero test. I'll be right back. Let's see what you got. So it just becomes all the possibilities of that plus or minus 20 divided by plus or minus 1, which is just all the possibilities of plus or minus 20, right? So those possibilities would be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. Right? All the numbers that divide into 20. Yep, that's all. All right. So the properties of the roots of polynomial equations. What that first part simply says there for 1 and 2 is that you can also have imaginary, that is complex roots. You can have, plus a plus or minus bi. So that may pop up as well. The fundamental theorem of algebra. Who proved the fundamental theorem of algebra? Carl Friedrich Gauss? No, I mean, I talked about it at the beginning of this lecture today, so it wasn't like something that I'm asking you to remember from 10 years ago. But anyway, Carl Friedrich Gauss proved it. He was about 21, 22 years old, proved it for his dissertation. He was actually proven, you remember we talked about the linear factorization theorem, and as one of the first cases for it, he proved the fundamental theorem of algebra, which says that any polynomial of nth degree has at least one complex zero or root. Pretty interesting. So, in other words, what that simply says is that any polynomial of nth degree can be factored at least one time. Now, he says complex root because you can have a function that never crosses the x-axis, but it still technically has a complex root. It can have imaginary roots. The linear factorization theorem says that any polynomial of nth degree can be factored n times. Again, this is what we've been doing in math for like ever. It's like one of the biggest concepts in algebra is, can you take up a function, an equation, and factor it? Well, the reason why you do that is because of the linear factorization theorem. Descartes' rule of signs. Here he talks about being able to determine the number of the actual number of zeros by using this concept. I'm going to have this on it'll be on the homework, it'll be in the quiz, but it won't be on the test in terms of making use. I think I have a problem or two here in the homework of making use of Descartes' rule of signs. I think just using the rational zero test and then using synthetic division, I think that gives you what you want. Well, let's look at this anyway. He says that the number of positive real zeros of f is either the same as the number of sign changes, and I'll show you an example of that, of the function, or less than the number of sign changes of f of x by a positive even integer. So part B, that first sentence in part B means this. Say, for example, in part A, if we got the number of sign changes is 3. And then he says, or is B less than the number of sign changes by a positive even integer. So if I got 3, so let's say here we get 3, then for part B, he's saying that the number is going to be 3 minus 2 to be 1. So less than or less than the number of sign changes of f by a positive even integer. So if it's 3, then 1 less than that is 2. So here he's saying that the number of positive real zeros could either be 3 or 1. If I had for part A, the number of sign changes is 3. And then he says, if, this sentence here, if f of x has only one variation of sign, then f has exactly one positive real zero. So let me cover 2, and then I'll tell you what I think, and then we'll move on, right? You don't want to ask me what I think, but anyway, I'll tell you what I think. Boy, have mercy. So the number of negative real zeros of f is either the same as the number of sign changes if you plug in negative x for x, and if the signs go from positive to negative, that's a sign change. If they go from negative to positive, that's a sign change. If all the signs in front of the variables, the coefficients, are all positive, there's no sign change. If they're all negative, no sign change. Again, I'll show you an example. And then he says, or, do the same thing, or less than the number of sign changes of f of negative x by a positive even integer. If f of negative x has only one variation in sign, then f has exactly one negative real zero. I mean, this is good. This is okay. But, I mean, who really cares about it? We can get what we want by, like I said, using the rational zero test and using synthetic division. That's what I've been doing for years, and it's never failed me yet. So again, I will not test you on Descartes' rules of signs. Again, it'll be on the homework, possibly on the quiz, but not on the test. And when I say quiz, I'm talking about the quiz in my math lab. The quiz that I will post in Blackboard is a subset of that quiz, and the quiz in Blackboard basically represents the test. So here's what he means by these sign changes. So what we're doing is you're looking at the signs here. this sign, right? That sign, that sign, that sign, that sign. So when you go from that 3 to that 2, a sign change. That's 1. And then you go from here, this negative x to the 4th to this 7x squared, sign change. So that's 2. And then here we go from plus to negative, from x minus 3, a sign change. So we have here 3 sign changes. So he says that there are 3 positive real zeros, or it's going to be 3 minus 2, that is 1 less than the 3. That's just based on this statement back here. That's what he's saying here. So it's either going to be 3 positive real zeros, or it's going to be 1. When he says positive, he's saying this. That x is like equal to, let's say, 4, or x is equal to 7. Then on that other part, he talks about like a negative real zeros, like x equal to negative 3, or x equal to negative 2. He's just talking about negative numbers and positive numbers, that's all. Okay, so, and then the other 2 examples, more of the same. Here, notice from the 4 to the 2, there's no sign change. But from this 2 to the 3, sign change, right? It's negative 3. And then from negative 3 to x, there's a sign change. So just 2 sign changes. So here we have 2 positive real zeros, or he says here, or there are 2 minus 2, which is, I think, misleading, because since we have 2 here, you would think that it would be 2 minus 1, 1 less than that positive number 2. So I would think it would be 2 minus 1, that we would get either 2 or 1 positive real zeros. If, look at that last one, there's only 1 sign change, and so you keep it at that. There's only 1 positive real zero. What's less than that, or 1 minus 0, which is still the same thing. There's only 1 positive real zero. I thought it was interesting in the book. He gave this example for the positive real zeros in terms of an example, but he didn't give one for the negative. So let's look at this one. Here's a problem here where, look at this function f, that the signs don't change, right? It's positive, 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 positive. So here, because he makes a statement, because all the coefficients are positive, there are no variation in signs, thus there are no positive real zeros, right? If there's no variation in signs, then we don't have any positive real zero. Then you test the negative. So what we're going to do here is just replace the x with negative x. So this x here is going to become negative x. And then just simplify that. And so now we look at the sign change. It changes 1, right? And then here it changes 2. So we have 2. 1, 2, I'm sorry, 3. That's a negative x to the third. So I didn't count that. So that's 1, 2, 3. So we have 3 sign changes, or it could be 3 minus 2. It could be 1. So let's look at the next page. And that's the problem. So here he has either 3 or 1. Well, let's look at a problem and go from there, and I think that's how we get it. Use the rational zero theorem to list all of the possible rational zeros for the given function. So it becomes all the possibilities of the plus or minus 8 all over plus or minus 1, which is just plus or minus 1, plus or minus 2. Here, plus or minus 4, plus or minus 8. So which one is that? Is that A? Everybody's good with that one? All right. Let's look at this one. Use the rational zero theorem to find all the possible rational zeros. So we look at all the factors of plus or minus 10 all over. Here are the numbers we're looking at. Possibilities of these numbers divided by the possibilities of that number. So plus or minus 10 divided by plus or minus 5. Let's list out all of these factors. Plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. All over plus or minus 1 and plus or minus 5. So I'm going to take each term in the numerator divided by the first term in the denominator. So we have plus or minus 1 divided by plus or minus 1, which is just 1. So that's plus or minus 1. And then we have plus or minus 1 all over the 5. Now I go to the 2. So it's plus or minus 2 over 1. So that's just plus or minus 2. Then plus or minus 2 over 5 is plus or minus 2/5. And then I go to the 5. It's plus or minus 5 divided by 1, which is plus or minus 5. And then plus or minus 5 divided by plus or minus 5. That's plus or minus 1. But I already got it right there. Then I go to the 10. Plus or minus 10 divided by plus or minus 1 is plus or minus 10. And then plus or minus 10 divided by plus or minus 5 is plus or minus 2, and I already have it right here. So we got plus or minus 1, plus or minus 2, plus or minus 5, and then we got plus or minus 10, plus or minus 1/5, plus or minus 2/5. Yep. Looks like C. Does everybody agree? See that? Good deal. All right. So here the following function is given. List all the rational zeros that are possible according to the rational zero theorem. Okay, go ahead and tell me, what are they? Let's start with the first one. Plus or minus what? 1. Always plus or minus 1. If we can't get anything else, we ought to get that one, right? So that's right. So plus or minus 1. Basically, what are the factors of that 45? So plus or minus, what's next? 3.
5.
Plus or minus, well, you got 3, but then, okay, 5, yes. What else? What about 9? You say 9?
Oh, yeah.
9? Yep, I heard that. Good. All right. Is it 15? Yes. What else? 45? All right. All right, good. So you'll put those in part A, and then it says use synthetic division to test several possible rational zeros in order to identify one actual zero. So we're going to take synthetic division, list these terms out. That's the 1 for the coefficient for x to the third, -5, -9, 45. All right. So let's start with the 1. So we start with this, with the 1 here. So we bring down this 1. 1 times 1 is 1. We get -4. 1 times -4 is -4. This gives us -13. 1 times -13 is -13. I don't get 0, right? So I know that 1 is not a 0, right? So let's test let's say what, maybe the negative one, and then we'll go to 3. Bring down the 1. Negative 1 times 1 is negative 1. Get negative 6. Here we get 6. Negative 1 times negative 6 is 6. Negative 3 gives me 3. I don't get 0. So now let's go to the 3. 1, negative 5, negative 9, 45. So let's test the 3. Bring down the 1. 3 times 1 is 3. Negative 2. We get negative 6. This is negative 15. Negative 45. Aha! We got a 0. Got a 0. So here it says just give one of these guys. So we say 3. We got that one. And then it says for part C, list all of the actual zeros. You're going to start from here and you can go down. Right? Just continue with synthetic division. So sometimes you can test that same number. It may work again. Or you can go to the 5 or minus 5. Let's test. I'm going to test the 3 again. Let's see. Bring down that 1. We get 3. It gives us 1, 3. That doesn't work. I'm just going to erase right there. Let's try negative 3. Bring down. This is a 1 there. So this is negative 3, negative 5, 15, 0. Boom. We get it. So here's what this says. This guy says that x is equal to 3 is a 0. This says that x equal to negative 3. And look at this factor right here. This is x minus 5 is equal to 0. So that implies that x is equal to 5. So I have 3 zeros, right? And they are the 3, negative 3, and the 5. And they come out of this big set. So I list here 3, comma, negative 3, comma, 5. Now notice here that n is equal to 3, right? Our degree is 3. So that means that the actual number of zeros can't be bigger than 3. Right? So notice here for this one, we actually had 3 zeros. Sometimes you know if you have x to the third as your highest exponent for that polynomial, you could have 3 zeros, real zeros, or you could have 1. And if you have 1 real, then the other 2 are probably complex, imaginary. Right? Let's keep digging. All right. So let's see. Do that one. Let's see what you come up with for this one. Kaylee, are you here? Kaylee? Okay. Something for you. And you said McKenna's not going to be. Okay, McKenna. Okay, I'm sorry. Lexi. So which one did y'all get?
First. Oh wait, no. The third one.
Is 6 a factor of 45? What'd you say? D is D. D would list them all. Yep. Make sure you get those factors, right? Factors of that 45, so that'd be what, 1, and then what, so plus or minus 1, plus or minus 5, plus or minus what, 15, right? What are the factors of 45?
3.
And then you get 9, right? Plus or minus 9, you gotta have that one. What was that?
3.
3, okay, yes sir, 3, that's right, you're exactly correct. So you got what? So it's 1, 3, 5, 9, 15, and then what, 45?
Yeah.
And then that's all over plus or minus 1, plus or minus 7. And you divide each term in that numerator by plus or minus 1, divide each term in the numerator by plus or minus 7. And then part D here would be all those possibilities. Okay. Very good. Maggie, did you correct that? Hey, Devin, let me get that test back. Bless you. Did I get somebody test number 3? Here's what I'm going to do, and I told others in the beginning, I want to let everybody know. So for test number 3, when you looked at it, only check the ones that you had right. The ones that you missed, I didn't check. I'm going to send these tests over to the testing center. And you have 1 week from now until next Thursday to go to the testing center and get these problems correct. Now for the softball young ladies, you have likewise until next Thursday to take test number 3. Okay? And if you didn't take it, just go to the testing center and there'll be a test for you and you can take test number 3. So between now and next Thursday. Okay? And oh, by the way, you know, if you're going to mess up on a test and do bad on that, but do bad on everything else, that's cool because I do drop the lowest test. So if one of your tests is bad, you know, let's kind of chalk that up and just make sure that you make good on all the others. Okay? All right. Now that problem keeps on going. So it says use synthetic division to test several possible rational zeros in order to identify one that actually works. So synthetic division. So we're going to list, that'll be the 7, -5, -63, and then the 45, right? And so you know you got we start off young, you know, plus or minus 1, test those, plus or minus 3, test those, see if one of those works, and then move to that plus or minus 5. So let's see, I'll test the 1. I'm sorry, 7. Then this is a 7, 2. That's not getting us anywhere. Right, 2. No, I'm not going to get 0. -7, -5, -63, 45. You think -1 will work? I don't think -1 is going to work, but let's just try it anyway. So, -7, -12. That's not going to work. Right? I'm not going to get 0 over here. So, kind of hunch that maybe one of those 3s will work. It's 21. So 16. 48. Negative 15. Negative 45. 0. That gets it, right? So then you got to test. I found that one. So you find the other two. We got x equal 3. That works. Right? So it says one rational zero of the function is, we got 3. Then part C, find the rest of them. So what are the other two? And again, you can start there, or you can just factor. But you can start there with that 7, 16, negative 15. What did you try? What worked? Negative 3? Negative 3 worked? Yep. Very good. And now what you end up with is this is 7x minus 5 equal to 0. So that gives you x is equal to 5 over 7. So we have 3, negative 3, 5 over 7. Does that make sense? Okay. So you see how they had that Descartes rule of signs? Didn't really use that. Just use the rational zero theorem, and then synthetic division, and just check. All right, so here we come to this. So use Descartes' rule of signs to determine the possible numbers of positive and negative real zeros. What are the possible numbers of here positive real zeros? That is, just look at the function. If you look at the function directly, do the signs change? No. So here for the positive, it's just 0. Oops. What about the negative? So here for the negative, we replace the x with negative x. So we have negative f of x is equal to, here that's negative x to the third plus 2x squared minus 3x plus 5. So we go from negative to positive, that's 1 change. Positive to negative, that's 2. Negative to positive, that's 3. 3 changes, or it's 3 minus one of those, 3 minus 2, we get 1. So it's either 3 or 1. Okay. Again, you know, for the sign change, you look at how many signs change, and then you take that number less than 1, so it's 3, you get 2, then you subtract 3 minus 2, that gives you 1. All right? I didn't come up with it. I don't like it, but I just put it there for the homework. Again, for this problem here, I will not have one of these like this on the test. Good to know. All right. All right, let's see what you come up with this one right here. Use that Descartes rule of signs to get first the positive number, possible number of positive real zeros, and then the possible number of negative real zeros. All right, what you get for the first one?
Be 3, 1.
Yes, sir. I love it. What about the next one? I got 0. What did you get? Maggie? You got 0 too? Replace the x with negative x. So we get f of negative x. So that's going to be negative times negative there. So that'll be positive 3x to the third. You know, positive powers always stay positive, so it's just plus 9x squared. That changes signs. That becomes plus 9x plus 7. There's no sign change, so it's 0. Right? Sign doesn't change. Right? Does that make sense? Sign changes, I noted. If it goes from plus to minus, that's 1, right? If it goes from minus to positive, that's 1. But if they're all positive, no sign change, 0. If they're all negative, no sign change, 0. All right. Here, find all the zeros for this guy. Here it says use the rational zero theorem, Descartes' rule of signs, and possible the graph of the polynomial function. Here's what I do. I just use the rational zero test and synthetic division, and I'm done. All right? So for the all possible, zeros, we get plus or minus 1. We look at the factors of that 14 divided by the factors of plus or minus 1. So that's plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. Right. So we take synthetic division. 1, negative 6, negative 9, 14. Right. So let's try the 1 first. So bring down this 1 automatically. 1 times 1 is 1. Negative 5. Here we get negative 5. Negative 14. Negative 14. Bam! Right? We get the 0. Very good. Now, notice that this is x to the third. So this is what I have right now. I have x minus 1. If I look at this thing factored, this is 1 times x squared minus 5x minus 14 is equal to 0. I mean, sometimes you can just take this part right here and just factor it without using synthetic division over there. That's fine if you want to do that. Looks like a 7 and a 2. negative, and a plus. So I get x equal to 1, x equal to 7, x equal to negative 2. Those are the answers. I don't need x anymore. X, I don't need you anymore. Is that an x or an alpha?